So, still on the basic inductor, let's look at physical characteristics of inductor and a little review of Faraday's law. You can see by the picture below what we're really talking about is what happens when we introduce a magnet in the open space, the coil of the inductor. Faraday's law was introduced previously, chapter 10, and we'll review it here for its importance in the study of inductors. And it will become even more important when we look at AC circuits. Michael Faraday found that by moving a magnet through a coil of wire, a voltage was induced across the coil, and that when a complete path was provided, the induced voltage caused an induced current. So, if you will picture this magnet moving in and out, what's happening is the magnetic field is expanding and collapsing, and that's the beauty of a coil in an AC circuit. As long as the current is changing, we've got some activity within the coil. That's our di by dt. So the amount of voltage induced in a coil is directly proportional to the rate of change, di by dt, of the magnetic field with respect to the coil. Where a bar magnet is moved through a coil of wire, an induced voltage is indicated on the meter. So the physical characteristics continued here. You can see now what we have is our induced voltage representation now relating to the number of turns and the change of the magnetic field. Now we have d phi by dt, where we had L di by dt. When a wire is formed into a number of loops or turns and is exposed to a changing magnetic field, a voltage is induced across the coil. The induced voltage then is proportional to the number of turns of wire in the coil, N, and the rate at which the magnetic field changes. The rate of change of a magnetic field then is designated now as the d phi by dt, where phi is the magnetic flux. The ratio of d phi by dt is expressed in Webers per second. Okay, again, keep track of these units and these measures in your notebook so that you can quickly draw on them and not have to go digging around trying to remember what they were as you read about them in your text. Faraday's law then states that the induced voltage across a coil is equal to the number of turns or loops times the rate of flux change. So voltage induced is equal to the number of turns times the change in the magnetic field with respect to time. So let's look at a little example. Apply Faraday's law to find the induced voltage across a coil of 500 turns located in a magnetic field that is changing at a rate of 5 Webers per second, d phi by dt. So there's our relationship. 500 turns times 5 Webers per second gives us 2.5 kilovolts of induced voltage. Lenz's law. Lenz's law, we saw in part A, the current is constant and is limited by R1. There's no induced voltage because the electromagnetic field is unchanged. In part B, a switch is suddenly closed, placing R2 in parallel with R1 and thus reducing the resistance. Naturally, the current tries to increase and the electromagnetic field begins to expand. But the induced voltage opposes this attempted increase in current for an instant. Okay, so there's our diagram that the paragraph was just alluding to. So we can see we've got two resistors being added into the circuit. We've got one in series, we've got one in parallel. So in C of the representation here, we can see that the induced voltage gradually decreases, allowing the current to increase. In part D, okay, so now we're down here in D, we've got the switch closed, the current and the magnetic field reach a constant value. Okay, so the current has reached a constant value as determined by the parallel resistors, and the induced voltage now is 0. In the next state, E, okay, so we're down here, at an instant when the switch is opening, the magnetic field then collapses, creating an induced voltage which opposes a decrease in current. Okay, so the switch has been suddenly opened, and for an instant the reduced voltage prevents any decrease in the current, and arcing between the switch contacts results. In part F, okay, the last step here, switch open, the rate of collapse of the magnetic field decreases, allowing the current to decrease exponentially back to its original value. Okay, so in F, the induced voltage gradually decreases, allowing the current to decrease back to a value determined now by the series resistor R1. Notice that the induced voltage has a polarity that opposes any current change. The polarity of the induced voltage is opposite that of the battery voltage for an increase in current, and aids the battery's voltage for a decrease in voltage. So we looked at a depiction here, or an example then, of Lenz's law. So this demonstration of Lenz's law in an inductive circuit, when the current tries to change suddenly, the electromagnetic field changes and induces a voltage in a direction that opposes the change of current. So go back, look at this explanation in your text, step by step, what's going on. Take a look at each of the depictions here of what's going on in the illustrations here. Take a look at the meters. The meters showing you, since it's in series with the inductor, what kind of current is occurring then with the battery, with the source in line. Okay, you'll notice here that as we close the switch, now we've increased the resistance. We've got the current changing, okay, I1 plus I2 current, which adds the current across R2, and then until that resistor, or that inductor's field, completely builds, because this is a DC source, we have I2 at a constant. Okay, so Lenz's law. In the next step here, in the next section here, we're going to look at different types of inductors. There are various types of conductors that depend on size, that can depend on what they're used for, different shapes. You can't use a big honking electrolytic capacitor in a tiny microcircuit. So we've got to have different types of inductors available when we actually build a circuit or design a circuit. So the inductors fall into two general categories: fixed and variable. We can see on the bottom a fixed, and the variable that has the arrow through it. We also have types that have air core, iron core, and ferrite core for our types of inductors. Pictorially, you can see the different types here. Some that actually look like resistors, some that look exactly like coils, and some that have some adjustments. The adjustments allow us to move the core through the center of the inductor and change its inductive value. So we need to look at, just like we did with resistors and capacitors, what happens when we put inductors in series in a circuit. And we'll take a look at that when we come back.